Okay. Hi, everyone. Thank you for coming. Thank you, 44Con, for having me. I'm Stiv. I'm a security researcher at Akamai. I originally joined as a threat hunter, and after a year and a half, I moved to the security research team. And before that, I used to do threat hunting and forensics, mainly on Windows machines. Now, over the past year and a half, even 2 years now or so, our team has been heavily focused on MS-RPC, but it's been mostly offensive research, like finding vulnerabilities, bypassing its security mechanisms, and stuff like that. We even presented some of our findings at last year's DEF CON and Hexacon. Now, this talk is a continuation of that research, but focusing mostly on the defensive aspect of things. So let's see. Our agenda for today is this. First, we'll see what exactly is MS-RPC and how it looks like behind the scenes. And then we'll do the same with ETW, which is a login mechanism in Windows. And we will need that because we'll be using ETW to detect MS-RPC-based attacks that are very common in the Windows domain. And lastly, because I don't want to limit our discussion to just detections, we'll see how we can supplement our defense and be able to respond or even mitigate some threats using another built-in mechanism in Windows called the RPC filters. But first, what is RPC? RPC stands for Remote Procedure Calls. It's basically a way of inter-process communication that allows programs to expose capabilities for other programs to call. That's the call part in Remote Procedure Call. And we'll focus on MS-RPC, which is Microsoft's implementation of RPC that is built into the Windows operating system, and it's been part of it since around the 90s. You might be wondering, if it's been around since the 90s, why is it still relevant? Shouldn't you focus on something more novel, like containers, cloud, AI? And to that, I'll show you this network map here on the screen. It's taken from a real-life network, not any test environment. And this network map is filtered to show only one fraction of MS-RPC traffic. And it's called the endpoint mapper, and we'll see what it is in a bit. So we can see here on the screen, I hope it's clear enough, that we have a lot of RPC traffic between every part of the network, and it's going on all the time. So yeah, RPC is still relevant for Windows domains. And not only that, it's also relevant for Windows attacks. This here is taken from MITRE's attack metrics. And I highlighted in purple all the places where MS-RPC plays any sort of role. So there's quite a lot. And it's probably not that legible, right? So just to give you some examples, we have techniques like PSExec or remote WMI for lateral movement, DCSync for credential dumping, vulnerabilities like zero logon or PetitPotam are over MS-RPC as well. And that's just a few examples. And if you want to have something that is more real life and not just a general technique, take a look at almost any ransomware report. Almost all of them had used the capability of PSExec or WMI or had that capability. So it's very much known, used, and operates. And RPC plays a big part of that. And this is exactly what I want to see in this talk, so how we can detect those attacks. Because those attacks, as they are harder to detect. Because RPC is another layer of encapsulation that we'll need to peel before we get to the actual attack data. And deep packet inspection is expensive, usually. So most network defense tools usually just show or parse the connection metadata, like source and dest and ports. Not only that, even if you wanted to see the process to tag the connection, most of them are running under SVC host or as protected processes. I'm talking about RPC servers specifically. So we'll have some difficulty matching traffic to the process or the process tag or operation. And lastly, RPC traffic can also occur over ephemeral reports or over SMB. So we can't really even create firewall rules to block them or restrict them because we either don't know the port because it's ephemeral, or SMB, it's SMB, which is critical to the operation of the system. And even if we wanted to have defense, we don't really have that many options. We have the RPC filters in the Windows firewall, and we'll see that in the last section of this talk. And there's already been some research around ETW-based monitors for RPC, but they're mostly been focused on the local side of things. And they didn't really take a look at the network aspect of the connection, which is what I'm aiming to show in this talk. The strongest option for RPC defense, in my opinion, is the RPC firewall, which was shown in, I think, Black Hat 2021. But it's a third-party tool. It requires process injection. It uses hooks. So there's some trade-off there. So how do we take this connection, which is PSExec, by the way, which doesn't tell us a lot of data about it, and turn it into something a bit more comprehensive that we can take a guess on? Well, first we have to understand how RPC looks like. Okay, so if I'll do my job correctly, by the end of this section, you'll understand the following terminology. We have the RPC interface, IDL and MIDL, and transport, the endpoint, and the binding. The RPC works in a client and server model. The client calls a function that is exposed by the server. On the screen here, it's foo as an example, but in real life, it will be create service. How does the client know which capabilities are exported by the server, and what can it call? For that, we have the interface definition language, or IDL. It's a text-based file that holds inside it the interface definition with its name and all the function that it exposes and their declarations. It also has a unique identifier, UUID, that identifies that specific RPC server. But that's just text-based. How does it get into the binary? Well, Microsoft created MIDL, which is a program that can take those IDL files and compile them into C headers and code wrappers that can then be further compiled into the actual binaries. But for connections to pass, they have to have some sort of endpoint, and that is the RPC endpoint. So servers can register an endpoint to accept connections, and the connections can be over various kinds of transports. On the screen here, we have the 6 most common ones. There are around 14 defined in the RFC, but most of them are obsolete. Those are the mostly used ones currently. And we'll focus on TCP and named pipe as our transports, because they're really the most common ones. And their endpoints, of course, for TCP support, for named pipe is a named pipe. Endpoint can also be either well-known or dynamic. In the case of well-known endpoints, they're well-known. Both the client and the server know what the endpoint is in advance and can just start communicating immediately. With dynamic, neither the client nor the server know what the endpoint is. Instead, they use the endpoint mapper, which is what we've seen in our network map. The server, when it starts, registers with the endpoint mapper and receives an endpoint. And the client, to know what an endpoint, it communicates with the endpoint mapper using the well-known endpoint, TCP port 135, and it then gets the endpoint of the server, and then they can just communicate normally. Lastly, we have the binding, which is the session between the client and the server, but for practical purposes, programmatically, that's a handle. And both the client and the server can manipulate binding and session attributes using designated functions that work on it. For example, authentication works exactly like that. Now, let's zoom into a bit in what exactly is being passed when we use RPC calls. So the client calls the function, but it doesn't really have or shouldn't have an implementation of that function because that would be counterintuitive. Instead, it goes into a function called NDR client call, which is implemented and exported by the RPC runtime, or RPC-RT4 DLL. The RPC runtime is the part in Windows that is responsible for all RPC operations and their handling, and the DLL is loaded into each and every process that uses RPC, whether it's a client or a server. On the client side, the RPC runtime is responsible for marshalling parameters, that is, taking the function arguments and making them network safe, connecting and resolving the remote endpoint, binding, authenticating if it needs to, and passing all the data. On the server side, the RPC runtime listens on all endpoints, accepts connections, establishes the session, gets the data, unmarshals parameters, performs any necessary access checks, and eventually passes control to the server function. Once that function finishes, the whole process is made the other way around to get the data back to the client. Now, if we zoom into a little bit more into what exactly is being passed to NDR client call and over network, we can see that in no point in time does the function name is actually passed to the runtime. Instead, what is passed is an integer called the opnum, which represents that function name or that function. And why is that relevant? Because in all our future interactions with RPC, we won't have the function name. We'll always see the opnum. So we need to have a way to match the opnum with the function name to understand what is going on. And it's not that hard, luckily for us. In most IDL files, which are documented on MSDN by Microsoft, most IDLs have the function opnum as a comment inside them, so we can just take it from there. And if not, it's usually made by the order of appearance of the functions in the IDL files themselves. So we can take the data from there, and we don't really have any issues. So that's it for RPC overview. So let's recap before moving on. We have the RPC interface, which is what describes the server functionality, and it's represented by a UUID. Then we have the transport, which is the communication medium, which carries the data between the various client and servers. And it's represented by protocol sequence like TCP or named pipes. The endpoint is the destination we connect to for our RPC connection, and its type depends on the transport. So we have a port for TCP or UDP, we have a pipe name for named pipes, etc. And lastly, the binding is the session between the client and the server. And it's represented by a handle on both sides. So let's move on to see how we can detect or see what exactly is being passed or requested with RPC. For that, we will be using the ETW, or event tracing for Windows, which is a built-in tracing logging mechanism in the Windows operating system. It worked in a provider and consumer model, so providers, those that generate events, define a schema so that clients or consumers can know how to parse their events. And both providers and consumers have to register with the ETW, which is implemented in the kernel. But the user mode logic that is exposed to both providers and consumers is implemented in NTDLL with some pointers in ADV API DLL. The flow is very simple. First, providers have to register with the kernel or the ETW, and you do so by calling event register and providing a UUID that will identify that provider. If all parameters are correct, the kernel will return a handle that will identify that provider on subsequent calls, for example, when writing events. But since there are no consumers registered, event data is discarded and being sent to the void. And we don't want that normally, because hopping the kernel boundary each and every time and also transferring a lot of data, which is the event data, it's very wasteful when we just discard data. So instead, what we can do, providers can define a callback and give it to the kernel, so the kernel can notify the provider about its state using that callback. And then, instead of just writing blindly to the kernel to the ETW events, the provider can first check if it has any consumers and skip event writing if it hasn't. This is how the callbacks look like. And the second argument here is enabled, which is exactly how the kernel notifies the provider if it should generate events. So going back to our previous example, we have our application provider, and instead of just writing to the event, first check if it is enabled, and then doesn't send events because there's no consumers. Once a consumer registers using enable trace and providing the same UUID that the provider defined for itself when it's registered, then the kernel notifies the provider about its state change, and then events can be routed correctly and all is well. In our case, we will be using the RPC ETW provider, which is implemented in the RPC runtime. Now, you might be wondering, I said that the RPC runtime is loaded into each and every process that uses RPC, whether it's a client or a server. So is it an issue that we have multiple provider processes and multiple client processes that generate events all the time? And the answer is no, it's not an issue because everything is handled by the kernel, which is a third party. So it can handle all the multiple providers and multiple processes generating events to the same provider. Inside the RPC provider, we have 13 different events, but most of them are error events or debugging events, which are not that interesting. And we will focus on two events specifically, which are the client call start and the server call start. The events for call stop, client side and server side, are also interesting, but they only tell us the status of the call and not any other data. So we'll skip looking at them for this talk. So both server call start and client call start have the same schema, and it's shown on the screen here. And if we take a look at the first part of it, we basically have all we need to map RPC operations with the network flow. So we have the interface UUID and the procnum, which is the opnum, to tell us which operation is being requested. And then we have the protocol, the network address, and the endpoint to tell us where the operation came from and on which network flow. So pretty cool. We also have additional headers that accompany any ETW event, not just the RPC events. They're part of the ETW framework itself. And we have an activity ID, which is another UUID, that can be used to track event chains. So for example, on the same RPC call, we will have an event for call start, call stop. Maybe we'll have an error event, if there was an error, maybe some debugging events. And as long as they're all related to the same RPC call, they should have the same activity ID, which we can then use to correlate those events. We also have the process ID of the process that created that trace event, which is useful when we're talking about SVC host-based processes. And lastly, we have the timestamp, which is the timestamp of when the trace event was generated. Why is it necessary? Because all events are going through the kernel. There will be some time lag between when events are generated versus when we actually get to parse them. So instead of relying on the time we receive those events, to have a more accurate representation of the timeline, we need to use the timestamp from the event itself. So with this, can we move on to actually detecting attack and seeing cool stuff? Nope, we can't. Because server trace events lack some data. This here is the compilation of the RPC runtime function that handles server calls. And we can see here that it doesn't have, or it doesn't send to the event the network address. Instead a null. I have some guesses about why it's a null, but they're not that relevant for this talk. What's relevant is that we don't have the data on server call events, which kind of sucks. And you might be telling me, okay, so Steve, you don't have server events, fine. You use client calls, you didn't say that it's not there, and the network address is actually there on client calls. But I don't run null on client calls. Because we're looking for malicious traffic, so we have to assume that the client is somehow under the attacker's control. So attackers can tamper with those events there, and then we won't see the events. So we don't want to rely on clients. For example, attackers can tamper with the ETW events directly by either disabling them or changing the data inside them. They can also maybe use the client as a proxy and generate all RPC traffic on their machine and just tunnel it through it. You won't have ETW events then. Or they can just generate all the RPC traffic directly because it's a protocol. They can't do that. And then we also won't have ETW events. So for example, Impacket, a very popular Python library for network operations, also used by a lot of red teamers, it generates all RPC traffic in-house. No ETW then. And precisely because of that, I don't want to rely on client calls. I want to keep a look at server calls. So what can we do? ETW to the rescue again. I said we'll focus on the RPC, on the TCP and name pipe RPC transports, and both of them have very extensive ETW providers. So we can just take the network flow from the ETW provider and match it to the corresponding RPC traffic by taking a look at the endpoint, which should be unique to each RPC server. So for TCP, it will be a port, and for name pipes, it will be the pipe name. With TCP, it's very simple. We have an event for accept listener complete, which is when the TCP handshake is established and we have a connection. Inside that event, we have the local address and the remote address fields, and there are binary fields that hold the IP and the port of either the client or source or the destination of the traffic. So we can take the port from here, match it to the endpoint in the RPC event, and then we have our connection between, or correlation between a network flow event and an RPC event. With SMB, it's a bit more complicated because SMB can have multiple file operations on the same SMB connection. So we have to keep track of two events, actually. First, we have, again, a connection accept startup event, which happens when the SMB session is established between the two computers. Inside, we have the address field, which holds the data for the client IP and port. Then we'll see, eventually, the event for request create, which is a file operation. And inside, we have the file name. In our case, pipes are treated as files in SMB, so we'll see the pipe name there. If we want to match the pipe name to the address, and then match the pipe name also to the RPC operation, which would give us all that we need, we have to keep track of the connection GUID, which identifies that SMB session. Now, I know that this maybe not be that clear with just arrows and boxes, so let's take a look at what happens chronologically when we have an RPC call over SMB. So let's say we have an RPC call. The first event that we will see is from the SMB provider about connection accept start. And there we'll have the IP of the client and the connection GUID. After a very short while, we'll also see an event, again from the SMB provider, for file request. And then we'll have the connection GUID and the pipe name, because they'll open the pipe for RPC calls. And lastly, we will have an event from the RPC provider with the pipe name, the opnum, and the interface, which is what we want. If we keep track of all this data all the time, and then backtrack once we get the RPC operation, we should be able to match that RPC operation with the IP and pipe that handle this connection. And I did exactly that. I implemented a Python script that I call RPC visibility that subscribes to all three providers using the Python library PyWinTrace, and it sends all results to Neo4j for visualization and querying. But it could be easily extended to use any other database if you want to integrate with a SIEM, maybe. But my code is, my code. So it's spaghetti code to make any Italian proud. So I guess it's not really that production ready, but it's a very good example of what we can do with ETW on the context of detecting RPC attacks. With this, we can actually move on to attack detection and see some cool stuff. So let's start with the demo, because why not? So PSExec. If you haven't noticed, I really like PSExec. It's both a name of a sysinternals tool that gave the technique, an attack technique, its name. And how it works is it copies a service binary to the remote machine's admin share, and then communicates with the service manager using its RPC interface to create a service for that binary and then launch it to achieve remote code execution. So let's see. Let's start our RPC visibility solution on our victim and also on the domain controller in the network. And then we'll just launch PSExec. So it doesn't do anything spectacular. Just PSExec is going to connect to the victim, authenticate, copy the binary, and communicate with the service manager to launch that binary. For PSExec, that binary then listens on named pipes, and then accepts connections that tell it to run commands. In this case, I told it to create a message box with the word hacks on it. So we can see it here. But when we're talking about the malicious attack technique, they don't really have to wait for commands. They can just launch a malicious binary and just do what they want in the case of attackers. So let's see what goes on in the RPC visibility solution. So we have a connection from an unknown machine, which is my laptop, which I hope better simulates real-life operations, to our server, the victim, and we can see also that some connections from the server to the domain controller over the log-on interface, well, for log-on, because we did authenticate when we did the connection. So if we want to have a better detection tool or technique, we have to focus our discussion to the SCMR RPC interface if we want to detect that technique. And we can see that we also here, hope you see it, yeah, we see a lot of connections and operations. And we want to not have that much data when we try to detect a potential attack, so we can focus on a specific function and see if we can detect it. And I chose to focus on, sorry, on our create service. And the reason I chose to focus on create service specifically is because it should have the least amount of false positives. If you recall, said I used to do threat hunting, and I tried to implement this same detection as a detection technique, but without having the context of RPC visibility, and just by detecting connections to the service manager, which is a well-known process called services.exe. And I had too many false positives. Basically, there's a lot of watchdog monitors and servers in a normal network, and they all communicate with the service manager and try to query the status of services or launch them if they fell down, crashed. So it's a lot of false positives, and you don't want to run that. What should be a lot more rare is the actual creation of services. So that's why I chose to focus on this specific function. If we want to fine-tune the detection even more, we can also query for creation and then the deletion of a service. It's also possible since we also keep track of the timestamp of the operation. Here it is. And if we take a look into what our tool logged, it also logged a potential lateral tool transfer. How did I know that? Well, tool transfer requires SMB operations, requires file operations. And we already subscribe to the file operations events in the SMB provider. We just need to take a look at the access flags, which are also logged as part of the event, and see if we have any files that are being opened for write access with the disposition of create file or override file. And we can also fine-tune it to see if it's an MZ, either by its extension, exe, DLL, SCR, whatever, or if, because we have some time lag, which should, by the time we get the event, it should also have been partially written. So we can try to see if it is opened, open it and see if it starts with the MZ header or P header. So that's how I did that. It's just another example of the power of ETW. And we can do the same kind of techniques to other attacks. So I mentioned at the start of the talk, DCSync. DCSync works by connecting to the domain controller and pretending to be another domain controller and request to replicate the credential database. We do so using the RPC interface of the directory replication service, MS-DRSR, and specifically a function called DRS get NC changes. Now, connections to the domain controller in any normal environment are numerous. They're all the time, nothing to be alerted about. But connections over the directory replication service should be a bit more rare, although they do happen, even not just between domain controllers. But request of the NC changes, the directed replication, is a lot more rare and should also only happen between domain controllers or maybe a backup server and the domain controller. Therefore, if we just focus our detection on that, we should have a lot less false positives. Next example is PetitPotam, which is a vulnerability that made a lot of noise. Basically, it's an authentication coercion attack. What you do is you connect to the encrypted file system service and tell it to open a remote file. The EFS service, which is available by default, did not handle UNC paths correct. And when you gave it a UNC path, it would trigger an outbound SMB connection with authentication that attackers can then relay for their nefarious purposes. And the functions are numerous that had the vulnerability, but the POC focused on EFS open file raw or encrypt file SRV. Now, in most networks, that's okay because EFS isn't really being used by default, although it is available. So we can just detect on the call of those functions. But if we have a network that does have EFS being used regularly, then we'll have a lot of false positives because everyone is going to open files or encrypt them. And to deal with that, we can, again, fine-tune our detection to not just look at the file operation or the RPC operation, but also see if there's a subsequent RPC file operation in the SME provider, since, again, we're already parsing those events anyway, and see if there's any outbound SMB connection with a UNC path, which would indicate a potential call for or exploit of the PetitPotam vulnerabilities. And lastly, I'll show also, I'll discuss the task scheduler, which is very similar to PSExec in a way that we copy a binary and then just launch it. And instead of using the service manager, we just call the task scheduler and create a scheduled task to launch that binary. But whereas PSExec has to have a specific type of binary, because it has to be a service and it has to have some sort of behavior, task schedulers don't have that complication or requirement, and we can just launch even CMD to just download or wget to download the next binary and execute it. And again, similar to PSExec, I chose to focus our detection to our RPC register task and not any other task scheduler operation, again, to reduce the amount of false positives that we can get from watchdogs. So, all well, we've seen some very common lateral movement or attack techniques that are being used and how we can detect them using RPC visibility. But let's discuss complications. And for complications, I'm talking about DCOM. DCOM stands for distributed COM, and COM stands for component object model. Basically, COM is another form of inter-process communication, but instead of creating a server function that exposes capabilities, COM has it in the form of class objects. So we can define a class object, register it with the windows, and then when you need to just load that object into your process and use it. And the COM objects are implemented in various DLLs that are then either loaded to the calling process or to a specific host process if we're talking about DCOM. And for notable examples, we have WMI, we have MMC, we have ActiveX. And DCOM complicates stuff. And I'm not going to tell you exactly how. I'm going to show you. Because, again, we have already a visibility solution. Let's see how it works. So first, let's clean our database. So we have a clean slate to take a look at instead of dealing with the residue of PSExec. So we clean the database and then just relaunch everything and have an attack method that uses DCOM. In this case, again, I didn't really discover this attack. It's the first attack that you get when you Google DCOM lateral movement. So basically, it communicates with the MMC 2.0 DCOM object, or COM object via DCOM, and tell it to launch, and that MMC object has the function that to execute shell commands. Just tell it to execute shell command, we execute the exact same command as last time, just message box with hacks. And let's see how it looks like with decom. So we have a lot of operations here. None of them have any name that seems similar to MMC, right? So to do a better analysis, let's filter the only function names and order it by time. So we have server alive, some sort of ping. Then we have get class object, create instance, few more operations about over that object. Eventually, we have get names, get function description, and invoke. So this is basically how decom works. It creates it calls create object. It uses its own RPC interfaces that are unique to decom. So it creates an object using that. It calls this remote function create object for an interface. Eventually, it calls invoke and then release of that object. What we don't have at any point of time is the actual logging of the object that we are creating and the operation that we're calling on it. And ETW in this case is not a solution, so we don't have that data, and we don't have an ETW provider that tells us that data. Because decom ETW provider is a lot less documented, and from what I reverse engineered, it appears to have only events that are raised when we have errors. It might still be useful for threat hunting, but not for our purposes. And to just give you an example of how undocumented that is, this is a common decom event, no data whatsoever that we can understand. So in this case, what we want is to have some sort of context. And the context that we can do is get it from the process that handles the decom operation. The problem is that usually by the time that we get to the decom event, because of the time lag of ETW, that process is already closed. So to handle that, we can use ETW once again and register with the kernel process provider that gives us all the data about process events. And in this case, process launches. So what can we do is a bit more heuristics. Basically, a process by itself is not very strong indication of any investigation, to trigger any investigation. But a process that was involved in decom is a bit more of an indicator, especially if we have a baseline of what is normally being requested in the network. It will have false positives, but it's better than nothing, in my opinion. And if we want to even fine-tune that a bit more, we can even take a look at which DLLs are loading, because it's also part of the process provider. So for example, here, if we focus not on the process name, which is MMC in this case, since we're using the technique was with MMC 2.0, we can take a look at which objects are loading. It's not that interesting in the case of MMC, because MMC itself, the binary, handles the object. But in other COM objects, that is the case. For example, we can see that WinTypes is being loaded after the invoke operation. Okay. And to give one last example of lateral movement, we have WMI, or remote WMI. WMI is implemented over decom. It stands for Windows Management Instrumentation. Basically, we take various components of the operating system and represent them in models that we can then query or modify. And I want to focus on the process model that allows us to create processes. Its normal operation is to get the status of processes or running processes, but we can also use a process called create to launch processes. And so how can we determine which WMI operation is malicious, which WMI operation is benign? So again, the example is the process model. And if we run both commands and see what RPC operations are being requested, we can see there's a difference between the call create versus the query. And it's in the opnums that are being requested and also in the interfaces being used. With call create, we call the exec method operation, and we don't have the enumeration interfaces being loaded or used but they are being used in the query. So if you compare those two side by side and then take a look at what is going on in the network, we can maybe try to tag some maliciousness or raise some suspicions about various RPC operations based on the optams, even if we don't know the exact operation that is being requested. So this all leads me to the end of this RPC visibility section and to talk about its drawbacks. And the main drawback is that it's still only a metadata-based detection. We can't really differentiate good and bad flows just based on the fact that some RPC operation is being called. We have to have some sort of context or some sort of baseline into what is being actually made in the network on a regular basis. So it's still a heuristic-based analysis. And it can't really handle DCOM with any certainty, but it has some sort of visibility there as well. And the second major drawback is that we don't have any blocking. We only have visibility and detections. So I don't want to limit ourselves to just detections. What can we do to respond or mitigate some threats? For that, we will be using the RPC filters. The RPC filter is part of the Windows firewall. It's built into every Windows machine, and it is exposed via either NetSH or the Windows API. And here on the screen, we can see me interacting with the RPC filters and creating, a filter with it. And we can filter on various parts of the RPC connection in something called layers. So we have a layer for connections to the actual RPC interface, and it's dubbed UM, I guess user mode. But we also have connections or layers for connection to the endpoint mapper specifically, or even the addition of new endpoints. So in the previous example, I defined the rule, filter rule on the UM layer, so for connection to a specific RPC interface. And my filter is the interface UUID. In this case, I can tell you that it is the MS-SCMR interface. So this rule is basically a way to mitigate PSExec. What we can filter on is all the general firewall stuff that you can think of, like source and dest IPs, the endpoints, port if it's TCP, namespace if it's pipes. But we also have some more RPC-focused stuff, like the interface UUID, or even the user token that is being used as part of the call. They're all documented in MSDN, but we already have a blog post about RPC filters, and they're internals. And we have notes on our GitHub about all the filters and what they're being used for. What we don't have here is the optam. So we have some laws of granularity, but what we can filter on. So we can't filter on specific optams, which kind of sucks. So what can we do with RPC filters? And I have a few examples here, but since I'm no longer doing or never have been doing actual network defense, I'm pretty sure the people in this room that do so on a regular basis can have better thoughts about how they can implement RPC visibility and filters into their existing playbooks. But those are just a few examples. So if we know what is being used in the network on a regular basis, because we have RPC visibility, if we see that there are potentially dangerous RPC servers that are not being used, like the SCMR, like task scheduler, etc., if they're not being used, we can just block them in advance so they cannot be used by attackers. But that might be a bit scary because, again, we're blocking something that might be crucial to the network that we didn't see or didn't foresee. So we can also use the RPC filters as a sort of emergency button. Once we detect an attack using, for example, RPC visibility or suspect an attack, we can just have a way to deploy RPC filters across the network and then just block that lateral movement path until we clear the suspicions or conclude our investigation. And if even that is a bit too scary or might be too bad for network operability, we can maybe just block the compromised users or potentially compromised user, again, using the RPC filters because we have the user token field there. And that's my examples for that. I'm sure there are many more. And that's it, basically. So let's summarize before moving on to Q&A if we have time. So we've seen the RPC and how it works and how it looks like behind the scene. Then we've seen how we can see what has been requested using the ETW provider of RPC. And I believe it's really a treasure trove of information that we can't get anywhere else. And we can use it to get a gist and understand what is going on in the network on a regular basis. And also, because of our understanding, also detect potentially malicious or anomalous connections and RPC operations to alert us about potential attacks. And then we've seen how we can respond to incidents or even mitigate some of the risk in advance using the RPC filters. That's it, everyone. Thank you for listening. We have time for questions, then go ahead.